In this next video here, we're going to look and see how power is needed to overcome friction. Later on, we're going to have situations where maybe we push an object on an incline and there'll be friction, there'll be coefficient of friction between the object and the incline. So not only is power required for the object to gain height over time, there's also power required to overcome the friction. So what we're going to do in this video is simply look and see how much power it requires to overcome friction. So here we have an object on a flat surface. There is coefficient of friction of 0.5 between the object and the surface. The object is being pushed by a force F at a constant speed of 10 meters per second. The mass is 40 kilograms. So how much power does that take? Well, first of all, we have to identify all the forces acting on this object. So we definitely have the weight of the object acting downward, and then we have the normal force of the surface pushing back, the normal force, and of course the magnitude of the normal force is equal to the weight of the object, mg. Of course the direction is opposite. And that means, let's see, where's my purple pen right here? That means there's going to be some friction between the object and the surface. The friction is going to be directed in the opposite direction from the motion of the block, because the friction force tends to be a retarding force trying to stop or slow down the motion. So the definition of the friction force is equal to the normal force times mu, and since the normal force is mg, we can say the friction force is mg times mu. And so in order for this block to be pushed to the right at a constant speed of 10 meters per second, the force here, the magnitude of the force, has to be equal to the magnitude of the friction force, so that there will be no net force acting on the block, and the block can continue moving at a constant speed. Again, to get the block started, it will require a little bit more force to get up to speed first, and then once it's up to speed, then it will require a constant force to move it at 10 meters per second. So the power, by definition, is work divided by time, or we can also identify it as the change in energy over time. But notice that from that definition, you're not changing the energy of the block. The block is moving on a horizontal floor, meaning it's not gaining height, so the potential energy is not changing, and it's moving at a constant speed, so therefore the kinetic energy isn't changing. If the potential kinetic energy is not changing, then of course it would appear as if no power is required. But you do require power because you have friction there, and when you overcome the friction, you're actually using up the energy, using up the power to overcome friction. So in that case, it's better to use the definition power is equal to work over time, where work is equal to force times distance over time. And of course, distance divided by time is velocity, so in this case we can also write that's equal to force times velocity. And the force required here in this case will be equal to the force required to overcome friction. So all the energy that's put into moving the box is lost by overcoming friction. None of it is used to increase the energy of the block, either in the potential energy sense or the kinetic energy sense. All right, so this is going to be force friction times velocity, and the friction force is mg mu, then we multiply times v. So when we plug the numbers in there, what do we get? We get 40 kilograms times g, which is 9.8 meters per second squared. So we have mg, now mu is 0.5, and the velocity was going to be 10 meters per second. And let's see here, how much is that? That's 3,920 divided by 2, that would be, I think it's 1,960. Is that right? Yeah, 1,960 joules per second or watts. Let me quickly figure that out on the calculator, make sure I didn't make any mistakes. Equals 1960, that's right. And usually, if I make mistakes, one of the viewers will catch me and let me know through a comment. All right, so 1960 watts. If we want to convert that to horsepower, of course we convert. So we have horsepower at the top, watts in the bottom. 1 horsepower is 746 watts. So that looks like it's maybe a little bit more than 2 horsepowers. All right, so divided by 746 equals 2.63. I call it 2.6, so 2.6 horsepower required to push that block to the right at 10 meters per second. Okay, and that's how you deal with friction, and that's how you figure out how much power is required to overcome friction.